So I'm going to start. Let me make sure I can share my screen. Okay. Can you guys all see my desktop?
Yep.
All right. So let me blow this up a bit. So this is Pete's wonderful 7-day loop that he puts together of the mid-level water vapor. And I'm going to start this back over. I just want to kind of cover a broad strokes of the last week and then kind of zoom in on a few really interesting severe weather events. So this was starting last week. When the last briefing we were talking about some of the severe weather that was going on down in the southern plains. So let's start here. So after this initial blow up of storms, it was pretty quiet, at least in terms of severe weather for some time. You can see the ridging over the central US. There's a deep trough digging in with a cutoff low off the California coast. And then out ahead of that, we really see this ramp up in activity again, especially over the southern plains, over the Texas, Oklahoma area, at least in terms of severe weather. So for this briefing, we're kind of going to take a quick glimpse of what happened last week, kind of brush over this more quiet period at the beginning of the week, and then some highlights of things that initiated out ahead of this next round, ahead of this trough over a couple-day period. So let me switch over here to my slides. So this was last Friday. So there was talk of potential severe weather in the Texas, Oklahoma region. And sure enough, in the evening after our briefing and things ramped up, weather Twitter was going nuts. It seemed like everybody was chasing this thing. It was absolutely gorgeous. So there was there were verified tornado reports and large hail associated with the area that was kind of the focal point of some of the briefing last week, as well as some of the strong wind reports along the Gulf Coast that Alex talked about. But as I mentioned, it got relatively quiet. This was last week associated with that event. And then since then, the story has been this low off the southwest coast, and the focal point being here, the southern plains. So this is the area I'm going to focus on for a few highlight events before I pass it on to Andrew. All right, so just the two periods in particular, the 27th and the 28th. So on the 27th, there were some brief tornadoes that spun up in eastern Colorado, but I'm going to focus mostly on what was going on here in northern Texas. And then the next day, there were 3 hot spots for large hail. I'm going to focus on the Fort Worth and the San Antonio region, and then Andrew's going to talk a little bit about the Oklahoma hail. So this is just kind of the big picture and some of the key points we're going to focus on. You will notice that there were some hail reports up near Green Bay or north of Green Bay associated with a line of storms ahead of the front a few days ago. So there was some small hail associated with that as well. So I was kind of curious how we're doing so far this year, like where are we compared to some sense of climatology over the past, 15 years or so, 15, 20 years, in terms of both tornadoes and hail. I felt like so many of the briefings this semester, we really spent a lot of time talking about the severe weather outbreaks in the Southeast. And now this time of year, as we get into late April into May, we see a shift in the overall tornado probabilities. This is for any intensity being more of the central plains. And then this red line here is the number of local storm reports for tornadoes so far this year. You can see the real ramp up in March in the events that we talked about in many other briefings. And it kind of quieted down a little bit in April, with things starting to increase. So it'll be interesting to see kind of what happens over the next month or so. I haven't really looked at the long-term pattern that's expected, but that's just something that we're keeping an eye on. And then in terms of hail, similarly, if we look about this time of year in the climatology for hail greater than 0.75 inches versus more significant hail, you see again that we see this really concentrated in this area where you've seen a lot of the hail in the past week. So this is kind of consistent with climatology, and you can see that there is some possibility of hail, smaller hail in this region this time of year, but really we'll see the chances ramp up here over the next couple of months. So in terms of total hail, local storm reports, if the black line here is the average over these past 15 years or so, you can see we actually have fewer hail reports than we usually do this time of year. Again, I haven't done much analysis on the whys, but just something I wanted to check on to see where we're at. Okay, so just to give some highlights, first I wanted to focus on the briefly tornadic supercellular storm that also produced some big hail in northern Texas, just east of the Panhandle. And again, in these days, I feel like I live vicariously through weather Twitter, looking at storm photos, but a lot of people were chasing this absolutely gorgeous mothership of a supercell over Electra, Texas, which is just around this area a few days ago. So the time of this was about 22:15 UTC. And then there were some later tornado reports and hail reports just a little bit to the southwest of this region. Absolutely gorgeous. So naturally, I wanted to take a look at the radar from this time. This is just a snapshot. So this was the time of the actual photo. Kind of a little bit of a mess here. You can still see some remnant, broad mid-level circulation. But just a little bit before that, about a half an hour before, you can see kind of this classic supercellular structure. And then this is the velocity couplet, this broad rotation associated with the mid-level mesocyclone that we talk about a lot in class. So I just wanted to briefly point this out. I think it just had a very brief tornado, but just absolutely gorgeous supercellular structure near the Electra, Texas region. So what initiated this? So this was a kind of classic dry line case that we've talked a whole lot about in class. So this was the 18Z surface analysis at that time. So we got the cold front draped further west across Texas, and then these storms initiated in northern Texas along this dry line. At the head of the dry line, you can see 60 plus degree Fahrenheit dew points within this broad southeasterly flow out ahead. So this was broadly favorable. There was quite a bit of moisture. One of the things though, I took a look at a few soundings. This is the Amaryllis Sounding. And then a lot of times in class, we talk about looking at soundings, on the west side and the east side of the dry line. So this is just such an obvious example of a series of soundings in Amarillo on the west side of the dry line. Very dry. You can see that nocturnal inversion mixing out dry adiabatic lapse rates. This is just kind of a classic example of what we've talked about a lot in class. But west of the dry line, there's not a sounding immediately west there. The next closest one is over much further east in Fort Worth, Texas. So you can see there was, even at 0Z that evening, there was a substantial cap present. Most of the instability was elevated. So these storms really didn't persist or produce any sort of significant weather further east over this Fort Worth region. But if we were to look at, for example, the supercell composite parameter and the spatial distribution, you can see it was really tied back to this area associated with the dry line with these very high values that we talked about in class. So I just kind of going through this quickly. This is a nice loop. This is the visible overlaid with the clean IR channel. And this is just an example of these storms indeed firing up along that dry line. With this being our gorgeous supercell that I showed a little bit earlier. And then later on at night, there is some strong low-level flow. Here's 850 millibar, bringing in some moist air that helped sustain some of these storms a little bit further to the east overnight. But the bulk of the severe weather reports were further back, closer to the dry line where they initiated. All right, so just to kind of move along, this was, to me, one of the more extreme highlights of the last week. Just absolutely incredible and devastating hail reported across 3 different regions. And remember, these triangles are the large hail reports greater than 2 inches in diameter. So you see there's kind of two sections. And then I'm going to focus first on the Fort Worth area. So I didn't look a whole lot at this area, but I just did take a quick glance at the weather service in Fort Worth. So this is, the radar derived maximum estimated size of hail. So, take this with a grain of salt. This isn't necessarily ground truth, but there were indeed reports of greater than 3-inch hail along this swath just north of Fort Worth. And here's some examples of some of the hail that was reported. So you can see kind of as a comparison, nearly tennis ball size hail over this region. But I want to focus primarily on what happened near San Antonio. I think many of us had our eyes glued to the screen, so a little bit more on the extreme end of things. The hail that formed east of or west of San Antonio. So again, this is a radar estimate, hail size, hail swath. So not all of this, of course, is verified, but even still, there's these pockets of really high large sizes inferred from the radar. And indeed, certainly some of this was verified as these storms tracked eastward. So let's just take a few snapshots here. This was near Sabinal, Texas. So this is a snapshot of around this time, and talking a lot in class about here in 441 about some classic hail signatures. Here's you're seeing the high reflectivity values, the low ZDR, the low correlation coefficient, and here's kind of our classic 3-body scattering spike that we see associated with this hail producing storm. So this was certainly verified, punching through ceilings in areas just west of San Antonio. So here's a loop of what happens a little bit later. So here's Sabinal, where some of that was shown. That really large hailstone I initially shown was near Hundo, which again, this is just west of the San Antonio metro area. I want to go back and actually look at this case a lot more carefully, so I'm kind of hanging on to a lot of this to look at later. You see just absolutely fascinating merger of several storms in this region during this loop. So this loop is about a little under 2 hours. So you see the merging of this really, and then the formation of this really classic supercellular structure. You can see there the velocity couplet here in this later time period. Out ahead, you've got these cells forming out ahead and this southeasterly inflow, a really interesting merger scenario that just haven't had a whole lot of time to look at more than just kind of this cursory look. But this thing was warned, tornado warned, as it approached the San Antonio metro area, which is always of great concern. It did end up weakening as it encountered the western edge of the metro area, but along its way, along this pathway, producing that very extremely large hail that you're seeing in those previous images. And this to me is always super fascinating, because for anyone who watches a lot of radar data in Texas, oftentimes right around sunset, you can see the signature of the bats coming out at night. And one of the things that I was looking at just east, I often look at Austin, but this is not an atypical signature of right around sunset of the bats coming out. But in this particular case, it's really concentrated on this eastern side. So I guess the bats maybe are perhaps fleeing, this incoming storm. It's interesting to know kind of what they sense, but you see this pattern, and I zoomed in here too. For those who don't look at this as much, the bats have a really high ZDR signature, depending on their exact orientation of how they're flying. So here's just this was just a little aside that I found interesting, kind of spending some time looking at these different non-meteorological signatures. But so here's again, that supercell encountering the San Antonio area, and it weakens not too long after this. Pretty scary situation though, having a after sunset tornado warning near a major metro area. I'm glad it wasn't worse than what it was. All right, so a few soundings just to kind of set up the scenario for this case. So this is just west near Del Rio. So this is just west of San Antonio. So they released a 20Z sounding on this case. So just, a lot of things we've talked about in class, and those more familiar with thinking about severe weather environments. Here you can see that the easterly flow near the surface turning and increasing. Here's the really strong winds associated with the 500 millibars wrapping around the trough. this is a pretty straight, all considered hodograph. So there is a chance for splitting supercells. And again, going back and looking at the splitting and merging of some of these supercells will be really interesting to dive into a bit later. So plenty of speed shear, the bulk shear, we've got nearly 80 knots, plenty to support supercellular structures. There's a moist boundary layer, dew points are in this area are approaching 70. We've got our steep mid-level lapse rates. So this is an environment quite conducive for splitting supercells and the likelihood of hail. So one of the things I wanted to point out here is I was going back to try to look at where did these storms initiate? What was their initiation mechanism? And this is a key point here, is looking at these near surface and low level easterly winds. So for those who aren't as familiar with the topography of this region, these storms were forming kind of some of this upslope flow here just west of Del Rio in eastern Mexico. So the storms fired up here kind of over this elevated region from this easterly flow impacting it. And then it moved over this, moved eastward towards San Antonio. And really it was trying to figure out where's the most favorable environment in terms of instability and the shear over this region. So just looking very briefly, instead of showing you all the different maps, SPC's mesoscale discussion nicely overlaid a lot of these features. They issued a mesoscale discussion for this region for 22 to about 1Z. And just to highlight some of the key points that were being watched here, as you can see the high mean level CAPE values extending into this region. So, at least 2,500 joules per kilogram. There's considerable bulk layer shear. So the green are the 0 to 6 kilometer shears. You can see here we've got 60, 70 knots, et cetera, into this region. And the cool 500 millibar attempts aloft, really enhancing those mid-level lapse rates. All right, so just to put an end to this, really a fascinating case, but this is one to really look into and study more going forward. This is the SIMS satellite blog, just awesome resource to look at some satellite loops. And here is the red visible satellite imagery starting around 21Z. So this is when the storms are, again, initiating across that elevated region over northeastern Mexico, just before crossing over into the Del Rio region. Here is the clean IR, and with time, you'll notice that there's some numbers that will pop up. So it's the hail report overlays with time. So I'm just going to hit go here. So we'll see this initiation over the higher terrain. We see this, it continues with time. We've got this eastward propagation. You can start to see that increase in intensity as it moves into that more favorable environment. You can see these really cold tops, the overshooting tops seen here. You can see the really strong low-level flow coming from the south. And you can start to see some of these hail reports associated with some of these coldest tops. So here's when we're seeing 2.5, 4-inch hail as it's approaching the San Antonio region. All right, so as the transition into the next part of the discussion, so this is a screenshot at 1:30 UTC. So this is after these very deep storms here shown in the IR imagery are dropping hail, in the San Antonio region. The storms that had formed over Fort Worth that produced hail are kind of weaker as they move eastward, but you can see those pretty cold tops as well. And look at this rather relatively unassuming brightness temperatures over central Oklahoma. And this is where I'm going to pass the baton off to Andrew, who's going to talk about this event and its impacts as well. So before I pass on to Andrew, I know I went through this kind of quickly, but does anybody have any questions from this kind of first look at some of these severe events?
Hi, Angela. John here. Really interesting, as usual, and fascinating how the dry line seems to pay attention to the 500 millibar leading edge of cold advection. I swear to God. I mean, that map you just showed, they all went off right where you're starting to enter the strong gradient region at 500 millibars. Any comment on the on the middle and upper tropospheric forcing that may have been involved. It doesn't look like the advection is very strong. I'll grant you that, because the winds, unless those are shear, I think only they're just shear. So you don't know what the temperature advection and whether or not it's differential is occurring right on that spot or not, but it could be. Do you have any comment, any analysis on that yet?
Yeah, John, I think that's a great point, and I just didn't have a chance to look at any of that. So I think that's a really good point to bring up, and something I just didn't get a chance to look at. I would suspect that there was some upper level forcing, but yeah, I'm not even going to speculate at this point because I just didn't look at it yet, John.
Yeah,
so,
okay. It's really, it's intriguing looking structure. So that you're right. This is going to be a great case to look at in detail.
Yep. I see Brad's hand. Go ahead, Brad.
Yeah, Angela, really nice discussion. So to get hail that size, is that, I mean, that size hail is that coagulating or combining as it comes down? How many up and down times through the storm did that take, and what sort of vertical velocities can support that size hail?
That's a great question, and it's something that I feel like my 753 students should be able to answer now, because we were just talking about our current understanding is you don't need that recirculation, that many loops through the storm to get that size hail. Really, the key is enhancing that residence time. So the time period in that updraft, which can be supported not only by really intense updrafts, 40 meters per second or more in the most extreme cases, but also broad updrafts. So a lot of the work that's been done lately with looking at modeling and trajectory analysis is you really need to have that broad updraft in a broad area for the hail embryos to be advected into in that really great growth region with a lot of super cool liquid water. So it doesn't even require this extreme kind of numerous recycling that has maybe been shown in schematics in the past. It's really needing the buoyancy and the shear to support these broad, intense updrafts that can contribute to that. So that's the really broad answer to that. Did you have kind of a more specific follow-on question to that?
No, that's great. That's very interesting.
Yep. I love this hailstone. This is the Fort Worth one. I mean, you could see all of the accreted rime, along this really spherical initial hailstone. It's just absolutely gorgeous. There's so many interesting. So you can see you get this large hail, and even in the ring structure, that many people thought a while ago required that large recirculation. It's really just variations in the wet versus dry growth related to the liquid water content and the temperature in the cloud. So, yeah. I don't know if anyone cut that one open. That just blows my mind.
Look at that thing.
I know. There were injuries. I can't remember where. Maybe I don't want to step on your toes, Andrew. I think it maybe was in Oklahoma where there was some injuries of people getting.
Yeah, there was one on I-35. From what I read, a hailstone went through like a windshield and like hit somebody like in the head. So, and the person's doing all right, thankfully. But yeah, I mean, that's what the kind of hail, like that kind of size. I mean, it's really going to do the damage, and it's going to leave its mark. And windshields, glass just aren't going to have much of a chance against it, especially if you start driving it in wind. It's just ridiculous. All right, I will
let you take over.
Yeah, definitely. Okay, so I'm gonna see your faces real quick before I pop up. Oh wait, hold on a second. There we go. Okay. Throw this into present mode. Okay. So Angela kind of set the stage a little bit. I guess first off, I want to make sure, has everybody seen the slides that I have prepared?
Yes, I can.
Yeah, I can see him, Andrew.
Okay, perfect. So yeah, so really on, I think this was Tuesday evening, the 28th of April, we had three pretty incredible large hail events that impacted the cities of San Antonio, Dallas, Fort Worth, and then moving even further north up the I-35 corridor, kind of the South Oklahoma City metro area, and in specific Norman, Oklahoma. And, I'm going to be focusing in largely kind of on the Oklahoma part of this event, but just kind of bringing it out real world and creating kind of some of the context of what the impact of this comprehensive event's going to be. So early estimates, you know, from insurance companies are that this is going to be an event that exceeds $1 billion in damages in terms of all the hail damage that was done to residences and egg crops and things like that. And then also moving into the Oklahoma City area, I saw a stat this morning from the state farm agencies across the Oklahoma City area. There's already been 500 claims made in and around Norman for hail damage. And I guess, you know, kind of taking a look at some of these pictures that I'm going to show you shortly, you could believe why. So, you know, moving north here into Oklahoma, there were 19 reports of severe hail in total on Tuesday afternoon, which I was actually a little surprised by how low that number is. But what's really impressive, I guess, about the distribution spatially of these hail reports is just how clustered they were around Oklahoma City, and really how suddenly and abruptly they all kind of started to pour in. And these were hail reports that were coming in, you know, you're talking 2 to 3 inch diameter size hailstones. And the thing that's kind of forgotten about this cell that impacted the Norman area is that it was also packing 75-mile-an-hour wind gusts. So you take 2 to 3 inch diameter hailstones and throw them around in 75-mile-an-hour winds, you know, things like windows that are facing into the direction of the storm flow. It's just not, they're not going to hold up very well. So there were a lot of incidences, unfortunately, in the greater Norman area of, you know, people having siding damage, window damage. And this is, I guess, a useful reminder why they do tell you, even when there's severe thunderstorm warnings issued, to stay away from windows, because you would not want to be near your windows, you know, in a situation like this where you have hailstones coming in and glass breaking. So really just incredible images to see. And then the other big thing that kind of came out of this Norman event were the car dealerships that were impacted. So I've kind of marked here with gray arrows, you know, just so many incidences of, you know, rear windshields on dealership lots getting not blown out, but, you know, knocked out by these hailstones, you know, all sorts of damage to the body panels. It's just, it's a total nightmare. Like I said, you know, once this is all said and done between these 3 events in total, you're going to be looking at over $1 billion probably in insurance payments that are going to be paid out. But kind of, you know, focusing in on more so the meteorology now of this hailstorm just to the south of Oklahoma City in the Norman area. You know, this storm really formed and initiated early afternoon across southwest Oklahoma. And as you'll see in a few slides, it was likely tied to some boundary at the surface. And Angela and I were also discussing earlier this morning, perhaps went up along like kind of a gradient aloft in the equilibrium level temperatures. But main point is that this, you know, this storm produced the large hail in the 7 to 9 p.m. time frame across the South Oklahoma City metro, but it had initiated several hours prior. And I guess what made this such an interesting case to look at is that, you know, it kind of persisted, you know, and marched its way across Oklahoma, but then it just went so robustly strong so quickly. And really it didn't last too long in terms of the strength, but it was during this period of time, kind of again, between the 7 and 9 p.m. central, you know, time periods that really this thing produced the large hail reports in and around Norman, and really exploded in strength. So my portion of the talk here today is just going to kind of be diving into first identifying perhaps what was going on that allowed that instability to rise. And then I have a bit of a hypothesis as to like really why that might have happened, but I'm not 100% sure. So diving in, hold on one second. There we go. Okay, so here over the next 2 slides, I'm going to be showing soundings that were coming from different models. And it was a little frustrating putting this together because normally you're going to stick with one model and kind of march through temporally and kind of show the evolution, but there were gaps in data that I just could not get around. So I'm first showing you a sounding that comes from GFS analysis that was taken at 0Z on the 29th of April, so 7 p.m. Central from OU Norman. And you can kind of tell, and really the marker of this case is the thermodynamic environment wasn't super impressive. So, I mean, you're looking at a mid-level that has moist adiabatic lapse rates, if that, perhaps not even moist adiabatic. And then the low-level lapse rates are relatively weak as well. So I've kind of marked that here at 0Z with the red box. CAPE is at about 940 joules per kilogram. And what's interesting is if we move ahead an hour, the vertical structure of this profile hasn't gotten much better, but there appears to have been an instability increase. So this is now at 1Z or 8 o'clock in the central time zone, again, from Norman. And this is from a different model. It's called the OP40. It's pretty much initialized with rapid refresh data every hour out to 24 hours. So I think the CAPE here might be a little overdone, but the point or the message of that instability was starting to build across the Norman area, really leading right into these large hail reports is kind of the big takeaway. And it's subtle, but clearly there's instability building. So it obviously begs the question of, well, how is this occurring? So I first kind of went through this and just, wanted to track things out on a larger scale, see what was going on to kind of allow this convection to persist, and then what could have been happening to allow the instability to build in this environment. So looking sort of synoptically, so this is really starting to look more like a warm season type of pattern when you look at the surface analysis from the WPC at 21Z or 4 o'clock or in the central time zone on Tuesday afternoon. But there were some weak areas of low pressure situated across Oklahoma. And really, they were all kind of tied to a boundary that extended into Mexico, up through Texas, and then through Oklahoma. And really kind of turning our attention to the relevancy towards this case, we can see we had a stationary boundary as it was analyzed by the WPC, situated off just to the west of Norman at 4 o'clock Tuesday afternoon. But if we look and jump ahead to, hold on a second. Sorry, my mistake. Hold on, I gotta run back. Okay, there we go. Going to 3Z, so 6 hours later, we can see that this boundary marched slightly off to the east. It didn't move too far, but it marched slowly but surely to the east across Oklahoma. And this appeared to be at least a lower tropospheric kind of organizational feature that allowed this thunderstorm to develop around 4 o'clock Tuesday afternoon in southwest Oklahoma, and then march its way towards the Norman area. And what's interesting about the boundary itself is that if we move kind of through the near term right around this event, knowing that a lot of the hail reports came in around kind of 1 and 2 UTC in that hour, this frontal boundary appeared to become a little more active really right over Norman. So what I'm showing here is the 925 to 850 millibar Pedersen frontogenesis. And normally you'd show it kind of in that 1,000 to 925 to see what's going on right at the surface. But really, I think it's a little more illuminating in this case to kind of show what was going on just above the surface. So this is at 7 o'clock central. And if we proceed through the time steps to 8 and 9, we can see right over Norman, which is situated here in dead central Oklahoma, we can see that this boundary lit up and really became more active. So again, you're starting to think, well, that's probably an area where we have air coming together. We have some sort of convergence, and you start to think of things that might have allowed the instability to develop. It looks like kind of how active this boundary became in that near term right around the hail played a role. And then, if we kind of look at the instability going along with it, what I've shown here is the bulk Richardson number over the same 3 time periods. If we recall, the bulk Richardson number is basically just a quotient of the instability in terms of CAPE divided by the wind shear. And you have relatively high numbers that are building kind of right over that Norman area in that narrow corridor. And it kind of co-aligns nicely with that frontal feature becoming more organized just a little bit above the surface. So if I had to bet, part of what allowed that instability to kind of build locally right over Norman was probably this frontal boundary kind of becoming more active. And I want to step back because I had lost my train of thought and got it back. The first thing I was thinking when I looked at this was, well, was there other convection ongoing? Like, is there something going on there that could have allowed this to become more defined? But really, and unfortunately, I wasn't able to get radar data, but this was really the only storm kind of on the block around Norman. There weren't other thunderstorms in progress. So I don't think the activation of this boundary or the strengthening in terms of definition of this boundary necessarily was directly tied to ongoing convection elsewhere. I think, it was just strengthening kind of right immediately out ahead of where the storm was about to move into. So again, you had your Balk-Richardson numbers there, and
Andrew?
you can see that, yeah.
Sorry to interrupt. I just had a question. So with the front becoming more active, it appeared in the images that you were showing that there's these northerlies that you can see over Kansas and northwestern northern Oklahoma seem to strengthen or become more prominent at slightly earlier times. I'm wondering, or maybe they've always existed like that in that zone. But wondering.
Go ahead. What were you thinking?
Just wondering if that was if what triggered or what was responsible for those northerlies either being enhanced or kind of being persistent in that direction.
Yeah, I mean, I'm really not sure. This was a very interesting case because I was looking, kind of at that lower tropospheric wind field early on yesterday when I was starting to analyze this, and I don't have a good explanation as to why that might be. But you're 100% right that the northerlies are persistent, if not strengthening a little bit, kind of right around the time that the large hail is going up. And it would make sense if you have the northerlies strengthening out behind this boundary. And the southerlies really weren't doing too much strengthening of their own, but they were kind of persistent and well defined. It would make sense that you would have that boundary strengthening. So don't have a great answer. Obviously there was some sort of weak little low pressure system moving across Oklahoma, kind of the central region of the state, because you can make out the cyclonic nature of the flow. And it came out pretty well in the surface as well, which I haven't been able to share, but I don't really know why the northerlies would have strengthened. I don't have a great answer for that.
Thanks.
Yeah. So then moving on, so past the Balk-Richardson number, really the thing that was bothering me here was, okay, so clearly the instability built, but I wasn't really sure, why was it building? And this is kind of where I have more of a hypothesis at this point. I'm not going to say that this was the only factor or even a factor at all, but I think it might have played a role. And I think, if we turn our attention back to the OP40 analysis that was done at 1 UTC from Norman, we have some substantial backing going on in the wind field between 800 and 700 millibars. And I've circled it here. And, earlier this spring, we were talking a lot about the importance of a veering wind profile and how it's tied to warm air advection and all of that. But we also know that when you get backing of the wind with height, that's tied to cold advection. So, with this kind of backing going on in the 800 to 700 millibar layer, it's clear that there's some sort of cold advection going on in progress, kind of leading up to this time right before the storm really intensified. And as we know, if you even cool a profile just slightly above the ground, you destabilize it. So that's kind of one of the things I'm thinking that could have played a role in this rapid intensification over Norman. And to kind of back it up, I pulled up kind of as my last two slides, some temperature advection from 850. So this was at 0Z. Again, I'm hoping you can see my cursor, but Norman is located right here across the central region of the state. And if we move basically to within the hour of, really this storm strengthening and producing all the hail reports near and around 2Z, you can see that cold advection at 850 is nudging its way in from the west. It's not necessarily located directly over Norman, but it's kind of making its nudge. And I just can't help but wonder if even that little small degree of cooling kind of in that 700 to 800 millibar layer didn't help contribute to a local kind of boost of instability, which could have been responsible in part for this large hail. Again, we were talking about earlier, there was a lot of deep layer shear present over this region, and we know that can be very beneficial in terms of residence times for growing ice hydrometeors and updrafts. So, something this subtle in a shear regime like that could have been enough to get this done. But again, it's still a hypothesis for me. I would want to look, at more data before, I guess, signing my name off on it. But it's something that's interesting and something that is worth, I think, keeping in mind here as we kind of start to unpack this event. And with that, that's pretty much all I had. So I'll stop sharing my screen and I'll pass it off to whoever was planning on taking the forecast. But first, if there's any questions.
I got one, Andrew.
Sure.
Sorry, I had to step away for a second there. I think your attention to this region of extraordinary backing is right on target. The sounding has a little spot where the temperature goes out right there. And if you can eradicate that little bit of warming by cold advection, suddenly, your inhibition's gone down substantially. Whether or not it increases your CAPE is another matter, but if it decreases your inhibition, what does it matter?
Right.
You get closer to the finish line. So I think that's a really good insight.
Yeah. And I mean, it's tough because, when you have large hail like this, you immediately want to look at steep mid-level lapse rates, but that was just absent in this case across Norman. So, you kind of have to start digging in and looking at the smaller pieces potentially that could have contributed to something like this. And I don't know if it was the factor, but I think it could have been an influencing factor as that storm kind of intensified right over Norman and dropped all of that gigantic hail.
And unaffiliated regions of that kind of strong implied cold advection are probably rare. So I think this has, again, it feeds back into your analysis and your interest in the structure of the frontal zone, which is weak, but that doesn't mean all of its characteristics are weak. And so I think one of the things that would be interesting would be to really do a full-blown analysis of the structure of this thing right at that time, because the soundings point to one thing, your couple of horizontal maps point in the same direction. It'd be really nice to see a vertical cross-section through there or something. So yeah, it's good thinking.
Absolutely. Thank you.
Okay, thanks, Andrew. I'm about to start sharing desktop. And
awesome.
Okay, so we're going to say just a little bit about, this time last week, we were talking about a tropical cyclone, a typhoon that we had talked about the previous week, and I think the week before. So this is our third week that we've been talking about this. And we're talking about the possibility of an extratropical transition event occurring in the West Pacific to the east of Japan. And thanks to Pete, Pete was able to secure some of the GFS data. So I've done a GFS or a WRF model simulation of this transition. The GFS forecast prior to the transition, this was starting at 0Z on the 26th, and it went through about 24 hours is when the complete transition and the very deep storm developed. This particular cyclone in the global model forecast were deepening down to sub 940. I think it was like 938, somewhere between 938 and 941. And my WRF model forecast at a 30-kilometer resolution, we got down to about 951 or so for the most intense. But this was sort of right out of the box, just getting the data, pre-processing it, and then putting it into the model. So this is an unrefined study of this storm, or very brief, just a simulation of it, and a couple of highlights from that simulation. So what I want to first show you next, so this is sea level pressure. The next map I'll show you is from, things are slow, is a map at the initial time. This shows in red the 1,000 to 500 millibar thickness. White contours, as you can see here, are sea level pressure from 1,000 hectopascals and lower. And the color fill pattern is the 500 millibar absolute vorticity. And so we're going to see this very obvious upper trough that exists from Eastern Asia down into the West Pacific, just to the east of Japan. You can see in the white contours the sea level pressure minima associated with the remnants of Sirigai. And again, very prominent upper trough. And this interaction, again, was depicted in the forecast models late last week. And we're thinking, okay, this looks like it's perhaps going to occur. And the forecast went through. But if you recall, about a week ago or even 2 weeks ago in the forecast, this was not something that was anticipated. I'll say a little bit more about that at the end. But we're going to next just step through the animation and get a look at how this cyclone develops. My apologies, I have lots of windows here, so I want to make sure I can just step through it. But you can see as we step forward in this, the tropical cyclone gaining lots of latitudes at the base of this upper trough can kind of come in behind it. You can see the isobars just popping out of the surface as we deepen well now below 980 hectopascal. You can see in this configuration of how the trough is oriented relative to the surface cyclone. And again, these are 1,000 to 500 millibar thickness contours. You can see that there is significant advection by the thermal wind of this vorticity maxima that's upstream of the cyclone. So this is in a nice, very favorable location for development to occur. As we continue stepping forward, again, just an absolute beast of a deepening as it goes below. This is close to the maximum intensity. It's in the low 950s at this point, and it kind of bottoms out here at about 24 hours. I think it goes just a little bit more, 27 hours, and then the filling begins after that. So really intense cyclone. If we just let it loop, let the animation continue, you can see that really impressive transition. Now, at some level, you might argue that this is, these transitions occur. There's a lot of obvious features in this, but it's still worthy. The rapid deepening of the cyclone as it intensifies is something worthy of note. The structure, just beautiful structure of the cyclone, at least in these fields, make it worthy of note. But this wasn't, at least in the short term, a really big predictability issue, because you had kind of the big elements coming together. The remnants of the tropical cyclone providing a low-level vorticity source, a very vigorous upper trough that's in just the right configuration for an interaction to occur that's favorable for development. What more could you ask for? And so, nothing really to ask for. But what I've done is I just sort of asked the question, suppose we didn't know a lot of these details. Were there any factors that could have contributed to this cyclone being stronger or perhaps weaker? And that turned me to using a tool that we've been looking at over the last year, which is using the Advent model, which we've used for several years, but looking at it from the perspective of potential vorticity and looking at the sensitivity of it. And so I just asked one question to start off with: which piece, does anyone want to guess, was perhaps, if you had to further intensify the storm, deepen it a little bit more, where would you want to put your, what basket would you put those eggs in? Would you want to put them in the upper trough or in the remnants of Surigai?
Upper trough for me.
Okay. And why is that? What's your thinking?
I think the environment around the former typhoon is so poorly stratified that you really need to have some. So if you can insert within that environment a focused region of forcing, you're going to make the air rise without any trouble. And I think that's going to be the thing that's going to determine whether or not it deepens.
And you are absolutely correct, at least in the initial analysis of this. So this shows the sensitivity to quasi-eustrophic potential vorticity. Again, the scale will change a little bit on this, but the scale is the same, but the color bar will change a little bit, just as I wanted to highlight a couple of issues. So this is the sensitivity at the initial time in this forecast of the cyclone intensity at 24 hours. So I looked at, we're measuring basically the surface pressure of the cyclone, and using that as our response function, we're asking how sensitive is that surface pressure to changes in quasi-eustrophic potential vorticity at the beginning of the forecast period, so 24 hours earlier. So you see the sea level pressure isobars as well as the sensitivity to PV, and you can see we have these sensitivities on the order of about 2 units. I'm just going to say 2 because they're in units of hectopascals per second. In any case, this is the distribution, and you could add some more potential vorticity in this cyclone, or curiously enough, in this region of this inverted trough that extends to the north of the cyclone. It's kind of on the leading edge of a cold front. Those are the places you would like to place this potential vorticity. If you go into the mid-troposphere, again, the scale is now enlarged, so it's a little bit more sensitive in these regions in the mid-troposphere. You could still put a little bit to the northwest of the cyclone, but even more along the leading edge of this upper trough. So this is actually, this is the 1,500 millibar thickness in this particular image. And so you can kind of get a sense of the advection by potential vorticity now being placed in this region where it's going to have its biggest impact. And if you were to put more potential vorticity just to the east of Japan, in this region, downstream of it, there is certainly a favorable region for pressure falls to occur, which is the direction in which this cyclone is headed. And if you go finally into the upper troposphere at 300 hectopascal, this is, again, the scale is now from -9 to +9. This is the most sensitive region just off the Asian coast up here. So this is really a key area you'd want to look at if you wanted to intensify the storm. And I'm not sure why this is advancing. Okay, at 300 hectopascal. So comparing this with the earlier image here, again, it's multiples of, if you put a 1 unit of potential vorticity in this, it would have an impact that's about 4 times as small as if you put it in the upper trough. So John, your instinct is right. And perhaps it is this low stratification environment that just means stretching is going to occur favorably anywhere in that region. And so if we go to 12 hours into the forecast, you can see this sensitivity. Again, the scale is the same as it was earlier. This is 12 hours in the forecast. If you want to alter the forecast trajectory, this is sort of the same sort of configuration, putting some PV just upstream of the cyclone. This is the 750 hectopascal PV and thermal, and you can get the thermal wind out of this. Again, really nice configuration for that setup. And then this is the sensitivity to 300 millibar QGPV. It's actually come down a little bit. So this is with 12 hours left, where do you want to put, what basket do you want to put those eggs in? And it's changed a little bit. And again, these are analysis, these are products that were just kind of hot off the presses, but this will be an interesting storm to explore at some later point. And if there are any juniors or rising seniors that are interested in perhaps looking at this, there's some opportunities to take a look at this transition. I want to be very brief and get to the current and future forecast. Some interesting questions, concern what's the role of, this goes back to actually the prior development. This is something that there was a big MJO surge that occurred a few weeks before Surrogay's development. What role did that play in triggering the cyclogenesis? John and I have been talking, what are the origins of the upper trough that facilitates this transition? Recall, a couple weeks ago and last week, or it was a couple weeks ago when this was first in the forecast to deepen, like it was going to kind of mill about in the tropics and subtropics south of Japan for quite a while and kind of just spin down. But then late last week, we saw a transition in the forecast that brought the cyclone to the north, and we saw the extratropical transition occurring. So what was the origins of that upper trough? When did it come into the network of data? How did the forecast fracture occur that allowed this to happen? How dramatic a mid-latitude cyclone would we have seen without the lower tropospheric remnants of Surrogay? John's point about the fact that we don't have a, that it's, the stratification is weak. I mean, that's partly the remnants at some level, but if you could somehow get rid of the entire circulation, was it more just a favorable thermodynamic environment and stratification that allowed this rapid development to occur? And what are the downstream implications of this forecast transition over North American weather? Again, a couple weeks ago, we were anticipating no interaction directly with the mid-latitudes. Last week we saw it, but so far it seems like it's been somewhat muddled. I know that about shortly after Weather Watch last week, or during the weekend, there was actually some evidence in some forecasts that were suggesting enhanced tropical cyclogenesis south of Mexico beginning about a week from now, or this weekend into early next week. That's totally been brought out of the forecast. It no longer exists in the forecast. I'm curious what's happening there. What's the fracture? Was it because of this interaction with the latitudes that we're not seeing that happen? Was something about this Kelvin wave that had been propagating across the Pacific that it's fallen apart? Maybe because of this interaction? I don't know, but some interesting questions with that storm. So I'll stop there. If there are any quick questions, then I'll go briefly to the the forecast and beyond.
I just have one comment, Michael, or question on your third bullet point. They're all excellent questions. The third one strikes me as maybe the first time where a person could really argue strongly for doing a full inversion of the PV, not just for the winds and the balanced stream function and all that, but for the thermodynamic perturbation as well, and then take it out of your initial conditions. So I don't know if you could get the moisture out, but maybe you could, but it'd be really interesting to see if you take Surrogay out of the thing entirely, the whole big footprint of it, including its thermal footprint, would you get a major cyclone? And I'll put money on it, or I'll lay down my bet. I'll say no money, but I think this would have been a really almost not a very substantial storm without Surrogay, because this trough is too sharply curved. It's mostly shear vorticity, except right at the base. And I think that it wouldn't have spawned as anywhere near as major a cyclone if it hadn't had that environment and the low level vorticity to begin with. But that's just a guess. We'd love to do the experiment. That'd be fun.
Yeah, so that's something to look at. And again, if they're interested students, that might be something we could pick up in the fall. Okay, so let's now go to a brief description, look at the weather. A couple of things I'll put up, since this is our last official weather watch of the semester. We'll be certainly having opportunities for weather watch if there's a really big event that's occurring. But this is the forecast for May, June, and July that came out just almost a couple weeks ago. And the forecast for the first part of the summer was for the likelihood of above normal temperatures over much of the United States, with the exception of, or continental United States, with the exception of sort of western parts of Oregon and Washington State, and perhaps a wet period over the eastern United States into southeastern Wisconsin, likely above normal precipitation with a below normal band occurring from the Pacific Northwest down into the central, the south central United States. Sort of equal chances of above, drier than normal or above normal precipitation over the high plains down to the central Gulf and then over the southwestern United States. And I think for these areas, equal chances is better than below normal, because anything they can squeeze out this summer, they're going to need, because they're entering they've been in a rather dry period for a long time. And if you just look at the forecast for June, July, August, sort of the traditional summer months, this is kind of the same picture. So again, below normal, or above normal, excuse me, for the entire United States, dry in the northern part of the United States, wet along the East Coast, and interestingly, wet across southern Arizona. So it's something to look at, and we can reflect back on our weather watch early next fall. Couple things to note here. This is the climatology that Ed Hopkins puts together nicely. This shows the blue contours are the average temperature for the most recent decade, that's 1991 to 2020. Maximum temperature, minimum temperature. There's freezing, and you can see our temperature trends over the year, calendar year thus far. And we've been in sort of a nice warm period in the last couple of weeks, or last week or so, after that rather chilly period back in early to mid-April. In terms of precipitation, however, we are markedly below normal. We've been that way since mid-February. Ed Hopkins reports that as of 6 a.m. this morning, for Madison has only received 1.44 inches of precipitation, placing this month at this point, with the next few hours left in the month, the 24th smallest precipitation total for the entire Madison record going back to 1869. So this is a relatively, this is 24th driest. There was an instance, I guess, in April 1877. There it was at University Hall, which is now Bascom. Only a trace of precipitation was reported for the month of April. So this is this has been relatively dry, not the driest, but the top tier of dry months for us. And then for snowfall, well, there's not much to say about it by this time of the year, although we may see some at the end of next week.
If you look carefully, Michael, near the end of that, you can see the 1/10 of an inch that they reported on the snow map about a week ago. See how it kind of just ticks up there?
Right there, yep.
So
anyway, a little, nice point there. Thanks, nice catch there, Pete. I had noticed that. So yeah, so there is oops, I didn't mean to do that. So you can see the precipitations. These are really nice charts that are put up by the state climatologist's office. Okay, so we're going to briefly look at the forecast for Madison, and basically, in short, it's going to be a this weekend. In the short-term forecast, I'm going to, just because of time, I'm going to jump to the forecast to not really go over current conditions. Did have a couple of actually, I do want to just do this. So this is satellite imagery from this morning, visible satellite imagery, and you can see really kind of severe clear over the upper Midwest over us. You can see over the northeastern part of the United States and the northwestern Atlantic, just east of Maine and south of Nova Scotia. You can see these areas of, you can see cold advection, which is a nice example of that on this particular map. You see the high clouds moving off to the southwest, low clouds from the northwest. That's a nice backing profile, and you'll see that on the super peat maps. Cold advection certainly on just off the northeast coast of the United States. You can see also this broad cyclonic circulation over northern Mexico, facilitating some warm advection in this region with a huge area of precipitation we'll see on the radar in just a moment. There's our radar. There's that departing storm in the northeastern part of the United States with some wind and chilly rains, but this broad area of precipitation that's occurring across eastern Texas. And then some precipitation that occurred in our area yesterday afternoon. Briefly, we had a light shower headed to the east, south of the Great Lakes into the mid-Atlantic states, but relatively quiet pattern across the United States. Unfortunately, don't have the John's favorite meteorogram, but we do have a facsimile, a nice facsimile of it, and we'll have those back next fall. But I'll first start with the time height section. which really shows, today we're expecting with full sun, nice mixing. We'll get to 233, that's about 15. So probably get into the upper 50s today with nice mixing and the boundary layer becoming well mixed. And then you'll notice overnight, over the course of the afternoon, these isotropes sloping downward with time. So there's warm advection that's beginning to occur. Upper trough is moving out, warm advection is beginning to occur. And you can see that after midnight tonight, we're going to begin to see the winds turning out from the south and freshening up with strong warm advection. You can even see this really strong stable air that begins to emerge with the inversion, which will break through, but will be into much warmer temperatures. This is 303. So we're looking at possibly low, dare I say, mid 80s perhaps tomorrow with a strong southwest wind. So at least 80 degrees tomorrow. It's going to be a really nice day. The one complicating feature may be some high and mid-level clouds that come in that may contaminate our ability to get the full insolation during the course of the day. But a warm weekend, at least starting off. Going to and so you can I'll step through the GFS forecast again. Time is somewhat limited, and I know folks are busy preparing for exams, but here's this is around midnight, the southwest wind, you can see nice, strong, warm thickness advection. Get to tomorrow, that persists. And I'll just step ahead into tomorrow evening. Again, nice, strong westerly flow over us. It's going to be a nice, warm day. Get into Sunday. And still nice, strong, warm advection. You can see some of the precipitation of the Gulf of Mexico persisting with these showers that'll slowly drift northward over time. But things will begin to moisten up as well, with some precipitation eventually beginning to break out as this boundary that exists just to our north, that moist or high water vapor air is traveling northward. Eventually it gets lifted along the boundary, and that's going to cause some precipitation to begin to develop to our north. So some showers perhaps on Sunday, not as nice a day. And if we go ahead into Monday, kind of persisting during that. So kind of nice studying weather, but get out and enjoy tomorrow. Looking ahead toward the end of the week, I'm going to give you a couple of pictures. A nice East Coast storm, at least in the current GFS forecast. But curiously enough, if you go back and if we look ahead into the commencement day, for those of you that are graduating, congrats on that. Kind of like a brisk, chilly day if this forecast pans out. If you look at the forecast from 0Z last night, there's a slightly different story with some rain and snow around noon just north of us. Here's the forecast sounding. 33 and saturated. That would be hopefully we get a much different forecast that emerges with an east wind. But again, that's not a pleasant tease, but that's one solution from the GFS from last night. The 6Z run and the 12Z run offer a much more welcoming, decent weather. It looks like the showers may hold off if this is correct for commencement day on the 8th. The Eastern WF forecast, just to bring that in from 0Z last night, going out to 186 hours. Does have some ice pellets to our southeast during Friday night, late Friday, early Friday next week, but just chilly weather coming in for the weekend. So again, we still have the possibility of just cooler weather for next weekend for commencement day, but not but dry. So hopefully that's going to be the solution. The most recent GFS has gone to a drier solution. Well, I want to stop now unless there's something folks would like to see. Just again, have a wonderful week. And again, tomorrow's going to be nice and warm. Good luck with your exams. And, thanks to Angela and Andrew and all the members of the 753 this semester that were presenting some of the forecast discussions, leading those that were enjoyable and very thoughtful, and gave us some insight into some of the processes that you guys have been learning about and helping us better understand these mesoscale phenomena. And thanks to John for his wonderful work over the course of this whole academic year and leading the weather discussions and particularly the current forecast. That's been great.
Thank you, Michael. And thanks to everybody for your contributions. It's been a great year.
Yeah, and Pete for helping organize this whole enterprise and getting it on the web for us. This has been great.
Yeah, thanks.
Yeah,
everybody.
I wanted to give a extra plus. Pete, thanks for managing all this. And I hope next semester we can all do this in person. I'm excited to
Me too.
finally get the chance to do weather watches in person.
Yeah. I know last summer we kind of continued the weather watches through the summer on an ad hoc basis. I'm probably not interested in leading a weather discussion every Friday, but if anyone would like to lead, I'm happy to fire this up and facilitate it. So if there's something going on over the summer and you want to do it on any given week, just let me know and we'll set it up and get it publicized. But I think for the rule, we won't be doing it every Friday during the summer.
Safe to say. If it
Sounds
snows
good.
in the summer, I'll be game, but that's about it.
I think everybody's got enough fatigue that we don't need to do it every Friday. We can, it's getting to the point where we can probably almost meet somewhere outside and have an outside weather watch.
That's
Just,
right.
Go to a park or something.
Actually watch
Some
the weather.
hand-drawn maps.
Watch the weather. Yeah, right.
If we use our phones to show the maps that we want to display, that would be neat.
All right. Well,